Okay, so we're into the second set of answers for the practice exam questions which I'd set you. I'm going to attempt to run through questions 11 to 20. I'm a bit pushed for time, but I'll try and squeeze them in, so apologies if I rush a few. Just a quick word about how to do this. You need to read the question and try and answer it totally on your own. And then after you've gone through it, you need to go back and check it against what I've written here. I hope that makes sense. But yesterday in class, many of you were literally getting the questions that I'd written and just watching my video and filling in the gaps. You're not going to learn a lot doing that. You need to have a go using your own brain first. Okay, enough said. So as I said, I'm a little bit short of time, so I'll try and go through this reasonably quickly. We're going to do 11 to 20 if I can. So question 11, about a point light source 1.8 meters above a work surface. The illumination on the surface, so luminance, E equals I over D squared. Put the numbers in. The intensity of the lamp, the distance squared. Put that in your calculator and you should come out with 618 lux. Don't forget, if you don't like that really long word lux, you could write lux. Okay, so next part of that question was, what is that law? That is the inverse square law. So moving swiftly on to question 12, it's a variation of this and it uses some of the same information. So the same lamp, intensity 2000 candela, height is 1.4, but we now need the brightness here, if you like, point P, 4 meters along the working plane. First thing to do is to find this distance, and to find that distance you're going to need Pythagoras. It's a right angle triangle, you know two sides, find the hypotenuse. D equals the square root of, and it's going to be 1.8 squared plus 4 squared. Put that lot in your calculator and you should find that this distance, the distance the light is travelling, is 4.39 meters. Next bit, we need to know the cosine of this angle. Remember, that's got to be a number between 0 and 1. And it's this side divided by this side. It's the adjacent over the hypotenuse. So, cosine of that angle is A over H. If we put the numbers in, 1.8 over 4.39 comes to 0.41. There you go. So your final step is to use the formula E equals I cos phi over D squared. So if we put the numbers in, intensity of your lamp is 2000. Cos phi, we just worked it out there, times 0.41, and then divided by the distance squared. It's the distance the light travels. 4.39 squared. So you'll know this as the cosine law, hopefully. And if you work that out, you should come up with 42.5 lux. Okay, so the last bit of the question asks you to name it, and it is the cosine law. Right, so that's 11 and 12 rushed through. Let's have a look at some of the others, and there's quite a few bits for me to talk about and discuss here. Let's just see how we get on. Right, so question 13. When I wrote this, I didn't think it through very quickly. I was rushing away writing it, and I didn't write a very good question. I'll explain why in a moment. The question asks you to list 4 discharge lamps with the best at the top and the worst at the bottom. So a quick run through. Low pressure sodium is about 180 lumens per watt. High pressure sodium could get up to 120 lumens per watt. Low pressure mercury, typically 60 lumens per watt. And this is why this wasn't a very good question. Your high pressure mercury ranges from about 35 to 65 lumens per watt. So these two are too similar to give a sensible answer. You could argue all day whether you should have this one up here or this one there. So you could swap those over. If I wrote the question again, I'd say list 3 discharge lamps. So we'll take either one of those out, any one of them out. But this will make a bit more sense if we just said 3. So I hope that's clear. Let's move on to question 14, which is all about tungsten halogen lamps. So name 2 halogens used in lamps, and you really want to be looking for, apologies, that's a mess. So iodine and bromine. So those are 2 common ones, and that takes us on to the next part of the question. So you have to explain the halogen cycle as used in a tungsten halogen lamp. So just to speed us along, I've pre-drawn a really naff drawing. It wasn't meant to be A-level art. As long as you can communicate sensibly to me what an answer is, you'll get the marks for it. Okay, so let's have a look. I've got an outer glass bulb and I've drawn a really naff little filament, but it doesn't matter. If I remind you about the process that we're going to talk about, then what happens is when we heat this filament, a particle of tungsten is going to leave. So a particle of tungsten will leave that filament. And with the halogen cycle, it's eventually going to come around back to here. But what happens? So it leaves and it will meet the halogen. Let's write halogen. So there is halogen inside the glass envelope. So it will meet it and it will form a new molecule. That molecule will travel around. It will not stick to the glass, and it will travel around until it comes back somewhere and it lands back on the filament. At that point, these 2 particles, the tungsten and the halogen, will reverse. The tungsten will now stay on the filament and the halogen goes back into the atmosphere of the glass envelope. So you've got to try and explain that in words. And I've had a go at doing it. You can have a go at doing it in your own way. You may wish to number parts of it if you so desire. But let's have a look how I've gone for it. As tungsten particles leave the hot filament, they combine with the halogen. So that's this part here. So you could number that 1 if you like. So 1. So tungsten particles have left and they've combined with the halogen. These molecules, so there's the new molecule, travel around. They don't stick to the glass. So you could give that a number as well if you want. That's 2. If you like, it's not sticking to the glass. 2. And they return to the filament where the reaction reverses. So they come back to there. So this is now 0.3. If you like, reaction reverses 3. The tungsten, let me just change sheets of paper. Let's do that. There we go. So the tungsten particles become part of the filament again, and the halogen returns to a gas in the envelope. The cycle continues. It just goes on and on and on. So hopefully that makes sense. Moving on to the next question. So just to speed us along, I've written some of the answers in. The stroboscopic effect is where we are. Lamps such as a low pressure mercury fluorescent flicker at 50 Hertz. So if these lamps are used near rotating machines, such as a lathe or drilling machine, the machine may appear to be stationary. That's a problem because it presents a health risk, an injury risk. So the next part of the question said, how do you get around it? So in somewhere like a workshop, install three rows of luminaires, each on a different phase, and that reduces the flicker and so makes the machines appear to rotate still, so we don't get the stationary effect. An alternative method is use an anti-strobe luminaire, and if you read your notes, we have things called a lead lag fitting, and there are others. So swiftly on again. Question 16. Question 16 asks you to give a very simple application or a place where they're going to be used for each of the following types of lamp. And what I've tried to do is to avoid writing the same answer in lots of them. For example, high pressure mercury could be used in street lights, low pressure sodium, street lights, high pressure sodium, street lights, LEDs, street lights. I've tried to avoid writing the same answer every time. So tungsten is mainly domestic. A bulb in your lounge. So low pressure mercury, it could be used in domestic situations, but I don't want to write domestic again. It could be used in classrooms, which hopefully you're all aware of. Could be classrooms, a small workshop, and other locations. So I'm hoping that sort of helps you there. High pressure mercury, if you remember the examples that I've given you, it could possibly use for lighting in a tunnel. It could also be used for floodlights, perhaps against a stately home or a large building. That'll do for that. Low pressure sodium. These are the hideous orange things, the orange light that we get, and they are street lights. Just stress, I've said it's orange. Technically, the colour of the light is yellow. And speaking of which, that takes us to high pressure sodium, which is a more yellow light than that. It's more pleasant and more comfortable. And they may be used in all sorts of places, like a warehouse. Perhaps an outside five-a-side football pitch. Colour rendering isn't fantastic, but I have seen them used there. So metal halide, quite commonly nowadays stadium floodlights. And LEDs, bit of a cop out on this one. It's pretty much all of the above. It could be domestic. Oops, sorry, the paper's moving. Could be domestic, it could be street lights. I'll just write street. It could be display cabinets. It could be anything. Okay, so I'll move on from that question. 16, and let's have a look at question 17. I'm very conscious of the time. Right, so question 17. This is about a 100 millihenry inductor. 100 millihenry. You cannot ignore that in anything you do. So first part was to find the reactance. XL equals 2 pi FL. We'll talk about the marking of this in a moment. So there's your formula. Put the numbers in. 2 times pi times 50 times 100 times 10 to the minus 3. I'm just going to bring the calculator in. I hope you can see this. I don't know if you can. Let's have a look at it. So I want to do this. It's 2 times pi. So shift pi is over there. Pi is just there. 2 pi times 50 times 100 times 10 to the minus 3. So that's times 10 to the minus 3 equals. So 31.4 is what we're looking at. So that is where we want to be. So just some words to the Y's. This is XL. If you write XC, you won't get a mark for the formula, if there is one given. It may be marked perhaps 1, 1, 1 as an example. If it is, and you ignore this, you're going to drop a mark. If you've ignored that, you'll get the wrong answer, and that will drop another mark. You just need to be careful. Don't ignore that. Write it in there, use it in the calculator, and it all starts with the correct formula. Okay, so let's look at part B, which I've left. Let's move that out of the way. So part B, I've left a bit of space for. So a coil has a reactance of 78.5 ohms on 110 volt 50 hertz supply. What is the inductance? So we're going to use that very same formula, and I'm just going to make you transpose it. So I've asked you for the inductance, L, which is this, but I've given you the reactance. You have to transpose this. So L is what we want. If you remember one of the strategies I gave you in class, you can do the crisscross, leave L where it is, and all of this moves under there. So my next line will say L equals XL over 2 pi f. Put the numbers in, and from the question, XL was 78.5 over 2 pi times the frequency, which was 50 hertz. Run out of space, and if you put that in your calculator, you should come up with 0.25. Don't forget your unit, Henry. If you don't want to write this, you could possibly write, 250 millihenry. Both of these would be correct. Okay, moving swiftly on. Question 18. Part A. A 330 microfarad capacitor is connected to a 230 volt 50 hertz supply. What is its reactance? So similar to these questions, but I'm on XC, not XL. Formula, XC equals 1 over 2 pi FC. And the first one was for a 330 microfarad capacitor. Do not ignore that, or you will go wrong and lose marks. So 1 over 2 pi times the frequency, which is 50, times the capacitor, which is 330, times 10 to the minus 6, which is what micro is. Let me bring the calculator in, and I'll try and do that for you. Just hope, yeah, I have to put it up there. So the calculator's still on, and I want to use the fraction button, which is up there. In the top one, I want a 1. Then come down to the bottom line, use your cursor, and it's 2 pi times the frequency is 50 times the value of the capacitor, so it's times 330 times 10 to the minus 6 times 10 to the minus 6 equals 9.65, I will call that, equals 9.65 ohms. Okay, hope you got all of that. So if we move on to the next bit, which is question 18b, what is the value of the capacitor that has a reactance of 63.7 ohms on a 50 hertz supply? We're taking that same formula, XC equals 1 over 2 pi FC. We're going to transpose it. We need to find C, the value of the capacitor. And if you remember the basics of transposition, let me do the crisscross again. Then this goes up there. The thing you want to find must be on the top line, and this moves down underneath. So the next line will read C equals 1 over 2 pi F. And the XC has gone down. XC is on the bottom. Put the numbers in. 1 over 2 pi times 50 is the frequency. XC was, I've lost it, 63.7. Put that in your calculator, and I'll do that right now. So let's cancel that. Use the fraction button, 1 in the top, come down to the bottom line. 2 pi times 50 times 6, apologies, delete that, 63.7 equals 4.99 times 10 to the minus 5. Well, minus 5 doesn't help me a lot, and I need to move it to perhaps minus 3 or minus 6. Use your engineering button, eng. 49.97, I'm going to call that 50 times 10 to the minus 6. So 50 times 10 to the minus 6, or better still, let's call it 50 microfarads. That's the answer that you would be looking for. Right, so swiftly moving on. Question 19, so I'm okay for time. So question 19. Difficult for me to do this on camera, but I'll fiddle about with it. It says a circuit is supplied with 230 volts, 50 hertz. Don't worry about that. Its inductive reactance is 100 ohms. Its resistance is 60 ohms. Draw to scale. That's the bit that many people mess up. Draw to scale the impedance triangle. So if you remember, let me quickly sketch. R is on the bottom, X is up the side, and your result, the hypotenuse, is Z. That's your impedance triangle. So R is 60. Get your ruler at the ready and do something like this. So I hope I can squeeze this in. So 60, I haven't drawn that dead accurately, but you're going to do probably 6 centimeters. So this is 60 ohms. This is R. Up the side, you want 100. So measure it carefully. I'm rushing it. So do 100. There you go. So this is 100 ohms, and this is XL. And if you join them up, there to there, do it carefully, take your time. Then this is going to be Z, and if you measure it and you use your ruler, this will come to about 117 ohms. And it says state the impedance. Tell me Z equals 117 ohms. You've stated the impedance. Let's move on. Hopefully we'll get through question 20. I'm sorry, I think I've missed a bit out on question 18. Where's my paper going? Now, question 18, apologies for this, part C asks what type of power factor will this component have? It's a capacitor, it's a leading power factor. And an inductor would have a lagging power factor. Sorry about that. Question 20 again. So it's talking about coils of wire. So here we have an inductor. It has a resistance of 20 ohms, reactance of 38 ohms, and you've got 110 volt, 50 hertz applied. Determine the impedance of the coil. So Z is what we're going to find. And Z, with the information you're given, is the square root of R squared plus XL squared. Put the numbers in, and we've got 20 squared plus 38 squared, square root of all of that. Do that with your calculator, 42.9 ohms. So that's nice and easy. Part B. The current it takes from the supply. Ohm's law, I equals V over R. But it's not R. This is an AC circuit. It has Z. And you replace R with Z. Put your numbers in. V, 110. Z, 42.9. That's what we just calculated there. And if you put that in your calculator, hopefully you'll get 2.56 amperes. Right, I hope that helps you guys. Let me try and finish off this question right now. So part C, I'll squeeze it in the bottom right hand corner. So part C asks you for the power factor. Power factor, I could write PF for power factor. I could write cos phi. They mean the same thing. So cos phi equals R over Z. Put the numbers in. The resistance was 20. Z was 42.9. That comes to 0.466. No units. We're nearly there. Let me do part D. So this is still question 20, part D. So you're asked to find the phase angle. So the phase angle is phi. And on the previous page, the calculation we did was cos phi. So we're going to do the opposite of cos phi. That's cos to the minus 1 of that number that we had, 0.466. And if you do this in your calculator, you will get 62.2 degrees. Final step. Find the power consumed by the circuit. We know from the very early days that we started power, P equals IV. You could have had P equals I squared R. You could have had P equals V squared over R. We don't want one of those. It's an AC circuit. We have to take account of the power factor. So P equals VI cos phi. Put your numbers in. And I can't remember what it was. I think it was 110. 110 times the current, which you found, times cos phi, the power factor, which is 0.466. Let's get this out of the way. Okay, and if you throw that in the calculator, you should come up with 131 watts. Okay, that's me done for now. I'll try and post the remaining questions as soon as I can, guys. Bye-bye.